All right, last one for this chapter. We're going to do 2.14. So a piston cylinder device is initially filled with 100 kilograms of refrigerant 134A at 200 kilopascals with a volume of 12.3 cubic meters. The system is then cooled at constant pressure until the volume is half its original size. Determine the final temperature and the change of total internal energy. So, a few things to note, as always. This is a piston cylinder, so as with the other piston cylinder questions, the pressure is constant. We know that, and that's consistent with what's written in the problem statement as well. So that's one thing, meaning the pressure at state 1 is the pressure at state 2 is the pressure at any state you want. It's 200 kilopascals. Other thing is, as with some other questions, we're given a mass and a volume so we can find the specific volume. Now, we're also told how the volume changes from 12.3 to half of that. So the mass hasn't changed. That means we know the second volume and we know the mass at the second state as well. So not only are we able to find the specific volume in state 1, we're also able to find it at state 2. That combined with the fact that we know the pressure is the same in both states at 200 kilopascals means that we now know the state postulate is satisfied in both states. So enough talk, we can start doing the question. Here we go. So specific volume at state 1 is 12.3. It's getting cut off there. Let me just start a bit lower. Sorry. Okay, V1 is 12.3 cubic meters over 100 kilograms. All right, and that's going to be 1.23. I think I'm just going to open up the question on my other screen there. Yes, there we go. 12.3 divided by 100, so 0.123 meters cubed per kilogram. All right, and we know pressure 1 equals pressure 2 is 200. And we know that V2, because they reduced the volume by half, is also going to be reduced by half. So it's going to be half of V1. So it's going to be 0.123 over 2, 0.0615, 0.0615 meters cubed per kilogram. So they are asking, let's just remind ourselves what they're asking. They want to know the final temperature and the change of total internal energy. If they want the change in total internal energy, that means we need to know what it is in the first place. Okay, so let's go use the tables for refrigerant and find U1. And we're at 200 and kilopascals and 0.123 cubic meters. So let's go to the refrigerant section. I'm going to guess it's a superheated vapor. Let's see if that's the case. Pressure is 0.8. And yeah, definitely, we're in, what was our thing? It was 0.123. Okay, so our specific volume is very high. Let's see. Sorry, I'm looking at the wrong pressure. That's why. Sorry. We're looking for 0.2. There we go. All right, that's a lot better. Excuse me. So we see here we have an entry that's almost exactly what we have. So we're not even going to bother interpolating. It's 0.123. We have 0.123. Okay, so this is clearly the entry we're looking for state 1. Now the change in internal energy. So our initial internal energy is 261.26. So let's record that here. That's always kilojoules per kilogram. That's our initial total internal energy. But then our specific volume changes, right? And we can already see from the table we were just at that if we go down to if the specific volume goes to 0.0615, it's way below what we're going to have even here. So we're probably best off looking at the saturated mixture, not the superheated. So, but we know the pressure, right? We know the pressure stayed at 0.2 megapascals. So we're looking somewhere on this line. Does that make sense, specific volume-wise, just to confirm? 0.06, yes, it falls in this range. So we're happy. We know that we're right. Okay. Sorry, I just lost my train of thought. Okay. Thing is, we don't actually know our quality of this mixture. So to know the internal energy, we have to know the quality. But we can find the quality because we know the limits of our VF and our VG, and we know our own specific volume. So like we did in that other problem, whose number I can't remember right now, we're going to take our specific volume minus VF, so 0.123 minus 0.0007532, and we're going to divide it by the complete span VG minus VF, so 0.0993 minus 0.0007532. And we get 1.24, which makes no sense. So clearly I made a mistake in the calculation. That means our quality is greater than 1. So let me just recalculate that. 0.123 minus 0.0007532. Oh, one thing, I'm using the wrong specific volume. It should be 0615. I was using the initial one, excuse me. And let's divide that by the 0.0993 minus 0.0007532. All right, that makes more sense. And we're getting a quality of 0.62. All right, so let's just write that down just so we can note. We're saying x2 equals 0.62. So that means, let's draw it out here. We have this line, right, where we have at the left end we're saturated liquid, and the right end we're saturated vapor. Now, we know we're somewhere along the line. Initially, we didn't know how far along the line we were, being quality, but we just found it to be 0.62 of the distance along this line. And that means that the internal energy at the saturated liquid and saturated gas states were 0.62 of the way between them as well. So let's go have a look again at the table. And we will see the internal energy UF here and UG here. So basically we're at 36.69 plus 0.62 of the distance between them, being 221.43 minus 36.69. And that gives us an internal energy of 151.22. Here. U2 equals 151.23 kilojoules per kilogram. So again, we did exactly the same thing here. We know the value of UF, right? It was 36.69. We know the value of UG, which is 221.43. And we know that we're 0.61 of the distance between them. So what we did was U equals UF plus quality, which is 0.62, times UG minus UF. All right, and this equation is valid for quality. Sorry, this equation is valid for mixtures in terms of internal energy, enthalpy, and entropy, which we're going to talk about later in the semester. And the change in internal energy is what they're looking for. So let's just do quickly. U2 minus U1, which is 151.23 minus 261.26. So we clearly lost some energy, right? We lost 110.03. kilojoules per kilogram. So obviously some heat was removed from the system, so things cooled down, they got a bit more dense, the piston moved down, and that's why we're at half the volume we were initially. Determine the final temperature. Oh, so they want the temperature as well. Well, we're a mixture, so we can read it right from here. It's minus 10.09 is the temperature there. And I think that just about covers it. Yep, that's all we got. Thank you.